Okay, so I'm just going to be going through PON 9.9, properties of logarithms. And it begins by asking us to rewrite some exponential equations in logarithmic form. And so there are a couple ways to do this. One is to think about it as the inverse operation and imagine basically taking the log of both sides. And another way is just to sort of memorize the formula and say, well, the base has to be the same. Oh, that might be a little bit hard to see. Let's see here. Maybe I'll choose this color instead. The base has to be the same. So since the base of the exponent is 5, the base of the logarithm has to be 5. The logarithm is always equal to the exponent. And so that means that it should be log base 5 of 125 equals 3. We can check with our little sort of circle here. 5 to the third power is 125. Yep, that works. And remember that this is asking us the question, 5 to which power is 125? And that is certainly 3. Here, first we need an exponent. So remember that a square root could be rewritten as, and that's where you should be thinking, oh yes, that's 49 to the 1/2 equals 7. Instead of thinking about rewriting, one thing we could do is think about taking the log base 49 of both sides. So log base 49 of 49 raised to something, those are inverse functions. And so then you just get 1/2 equals log base 49 of 7. Of course, you could write it log base 49 of 7 equals 1/2. That's the same equation. 2 to the x equals 13. I could think to solve for x, what I need to do is undo raising 2 to it. And to do that, I take the log base 2 of both sides. And I end up with the equation log base 2 of 13, that's this, is equal to x. And of course, I could use my calculator at that point to find that value if I wanted to. Going the other way makes a little more sense to me. I don't know why, because now I know, oh, 4 to the second power is 16. So I should just be able to write 4 squared equals 16. Yep, that works out. And here I can write 5, the base, to the negative second power. This is always the exponent, is equal to 0.04. This should be the same as 1 over 25 because 5 to the negative 2 is 1 over 25. The last one had asked you to rewrite log base 10 of 4 equals x. I'm not really sure why they wrote log base 10 because it's really just log. But that helps us remember that this would be written in exponential form as 10 to the xth power has to be equal to 4. Okay, so whether you're thinking about rewriting it or maybe using inverse operations, like in this case, you could say 4 raised to this and 4 raised to this. That cancels out, so you get 16 equals 4 squared. Or whether you're just using your definition, that is converting between exponential and logarithmic form. So now we'll move on to what this section is all about, which is developing some properties of logarithms. And to do this, we're going to use our calculator. So I'll just get my calculator here and push this over a bit. So it's asking me to find log of 3 times 5. So remember, log is that button right here. So I can do log, and then I'm going to do 3 times 5. And that gives me about 1.176. If I do log of 3 and then log of 5, so log of 3 is that, then I'm going to multiply that by log of 5, I get 0.333. Okay, so clearly these two things are not equal. So that is important to know. The logarithm of a product is not equal to the product of the logarithms. Okay, we would like it to be true, but it's just not. The logarithm of a product is not equal to the product of the two logarithms. Okay, so you cannot assume that that's true. Well, let's see maybe some things that will work out. So first of all, let's find log of 4 times 7. So that's going to be log of 4 times 7, and that is 1.447. So 1.447. Now let's find log of 4 and log of 7 and add them together. So here's log of 4. We're going to add that to log of 7. And what do you know? It's 1.447. Interesting. Okay, so it looks like log of two things multiplied might be equal to the sum of the two logs. That is an equation that's true. Let's see if it still holds true if we use 6 and 9 instead. So coming down here, log of 6 times 9 gives us 1.732. 1.732. Then we will find log of 6, and we will add it to log of 9, and we will see that we get 1.732 again. These are equal. So it looks again like if you take the logarithm of a product, it is equal to the sum of the logarithms. Interesting. So number 3 just asks us to see if we think these equations are true. Well, we showed that this one is not true. This is false because the logarithm of a product is not the same as the product of two logarithms. We showed that this one is true. The logarithm of a product equals the sum of two logarithms. I'm going to guess that this would also be true because, again, we have a product inside the first, and it can be broken up into two logarithms that are added together. And we showed that this one was true as well. So those 3 are true. I don't love their choices of variables, so I wrote mine with different variables. But basically what we're showing is that when you add two logarithms, you can combine them into one by multiplying the stuff inside. Okay, not adding. And these are not being multiplied, but when you add two logarithms, you can combine it into one by multiplying the stuff inside. So I will write the log of a product equals the sum of the logs. We could also say 2 logs added together may be combined into 1 log by taking the log of the product of inside stuff. So the log of a product, the log of two things multiplied, equals the sum of the two logs. If you want to put two logs together that are added, you may combine them into 1 log by taking the log of the product of the inside stuff. That is the m and the n. Okay, let's see if we can figure out some more properties of logarithms. So now we've got a logarithm of a quotient, division, and we want to know, is that equal to the quotient of the logs? Okay, so let's find log of 43 divided by 8. That gives us 0.730. Now let's find log 43 and divide it by log of 8. And we get 1.809. Okay, so it looks like these two things are not equal. That is, the logarithm of quotient is not equal to the quotient of the logarithms. So let's see if it has a property kind of like the previous one, where a quotient might be subtraction. And you might guess that this is true. So first of all, let's find the log of 63 divided by 9. And that will give us 0.845, 0.845. Now let's find log of 63 and subtract log of 9. What do you know? 0.845. So these are equal. Interesting. Okay, looks like the logarithm of the quotient may be equal to the difference of the two logs. To double check, we could do log of 12 over 7. So log 12 divided by 7 is 0.234, 0.234. And log of 12 minus log of 7 is, what do you know it? 0.234. So again, these are equal. The log of a quotient is equal to the difference of the two logs. So we have shown that this is false, this is true, and there's a couple more that I'll let you think about whether they are true or false. But summarizing, we know now that if you subtract two logs, you can combine them by dividing the stuff inside. Or we could say log of a quotient equals difference of two logs. Interesting. So we've just developed two properties. Okay, going back. The first one is, if you have a log of multiplication, you can break it apart into addition, or if you're adding two logarithms, you can combine it into one by multiplying the stuff inside. The second one says, if you have a log of division, you can break it apart into two logarithms by subtracting, or if you have two logs that are subtracted, you can combine it into one by dividing the stuff inside. And this is a tool that is going to help us solve logarithmic equations and simplify expressions. All right, finally number 8 and 9, and then we'll wrap this up. So it says find log of 2 to the 5th. So log 2 to the 5th, whoops, is 1.505. Now let's find log of 2. Log of 2 is 0.301. Remember, that is the power of 10, which would get you 2. 10 to the 0.3 is 2. All right, let's try log of 81, which would be 10 to which power is 81? Almost 10 squared. And then let us multiply it by 0.5, because we were finding 1/2 times log of 81. And that gives us 0.954. Let's find log of 8 to the 2/3. Remember, 8 to the 2/3 is the cubed root of 8 squared, right? Cubed root of 8 squared. Cubed root of 8 is 2. 2 squared is 4. So that's actually just log of 4. So I'm going to find log of 4. And that is 0.602. 1/5 log of 32. Okay, log of 32 is that. Let's divide it by 5, and we get 0.301. Okay, interesting. 0.301, 0.301. Okay. 5 times log of 2. Log of 2 times 5, 1.505. Ah, interesting. 1.505, 1.505, same thing. I wonder if this is going to be 0.602. Log of 8 is that times 2 divided by 3, or 2/3, is 0.602. Oh my goodness, interesting, same thing there. And finally, log 9 is my last one, and let's see what that gets me. log 9 is 0.954. Okay, so now we got to do some thinking here. So let's match some of these up. So let's see here. These are the same. Looks like these are the same. Looks like these are the same. And these are the same. That doesn't really make it easier to see, but. So what I'm noticing is that log of 2 to the 5th is the same as 5 times log of 2. Okay, so if you multiply by something out front, it seems like something might be able to happen there. 2/3 times log of 8 is the same as log of 8 to the 2/3 power. Okay. Log of 9 is the same as log of 81, but 9 is 81 to the 1/2 power, right? 1/5 times log of 32 is equal to log of 2, but log of 2 could be written as log of 32 to the 1/5. And this could be written as log of 81 to the 1/2. So it looks like to me that n times log x is equal to log of x to the nth power. Interesting. So, to summarize, we have the product property, which says log of A plus log of B equals log of A times B. We have the quotient property, which says log of A minus log of B is equal to log of A over B. Add 2 logs, combine them into 1 by multiplying the stuff inside. Subtract 2 logs, combine them into 1 by dividing the stuff inside. And we have the power property of logs, which says n times log of x is equal to log of x to the n. If you multiply a logarithm by n, you can take the logarithm of that number raised to the nth power. So we'll spend a little bit more time thinking about why this might be true, but these are your 3 properties of logarithms so far. There's one other that says that, log of b divided by log of a is equal to log, I'm going to say log of a over log of b is equal to log base b of a. This is called the change of base formula, because you can change a logarithm base b into a logarithm of some other base, but that's sort of an additional one that we don't need to know yet. Great, so we'll talk about that a little bit more, but hopefully that's making some sense based on just plugging some things into our calculator.